Good morning. Now, the stereochemical aspects of SN1 and SN2 reaction. To understand this topic, you have to know some terms, that is the stereochemistry, that is stereoisomers. The stereoisomers are the isomers, the chemical compounds, for which same chemical formula but have different spatial arrangements of the bonded groups. ഒരു chemical compoundsലെ respective elementsന്റെ spatial arrangement ഉണ്ടാകുന്ന difference കൊണ്ടുണ്ടാകുന്ന different types of compoundsനെയാണ് stereoisomers എന്ന് പറയുന്നത്. They will show same chemical property but have some different optical properties, optical activeness. That type of stereoisomers are called enantiomers. By the difference in spatial arrangements of the respective elements of a group, of a compound, they show difference in their optical activeness. That type of stereoisomers are called enantiomers. For a compound to show some optical activeness, it will have two enantiomers. രണ്ട് enantiomers ഉണ്ടായിരിക്കും. One will be dextrorotatory and the other will be levorotatory. The optical activeness means it is the ability of an organic compound to rotate the plane polarized light to some extent of angle. For details, we can see a video.
From a source of light, the light waves, the transverse waves of the light will propagate in all direction, vibrate in all direction, and can simply represented as the arrow marks. And when a nickel prism is placed in front of this candle, some light waves vibrate in particular plane can only pass through this nickel prism, and the emergent light rays are called the plane polarized light. That is the light with a particular plane polarization. When this plane polarized light is allowed to pass through an optically active substance, that is a solution of an optically active substance, the emergent light from the optically active substance changed its plane of polarization to some extent, some extent of angles, and therefore we cannot view the source of light if a nickel prism of the same axis is placed there, and we have to rotate the nickel prism to some angle to view the source of light. And this property of this organic substance to change the plane of polarized light to some angle is called the optical activity. That is, there is a change in the plane of vibration, plane of orientation of this light to some extent, and that can be measured by using a spectrometer. And this, if the angle of rotation is in a clockwise direction, it is called a dextrorotatory, and if it is in the anti-clockwise direction, it is called the levorotatory. And this type of substances which has the optical activeness are called enantiomers.
The observation of Louis Pasteur that crystals of certain compounds exist in the form of mirror images laid the foundation of modern stereochemistry. That is, Louis Pasteur found that the optical activeness is because of the three-dimensional arrangement of the elements present in the molecule, that is the configuration. The three-dimensional arrangement of the molecule, the elements of the molecule, is called the configuration. The configuration of a molecule is fixed. Dutch scientist Van Hoff and French scientist Lebel in the same year, that is 1874, independently argued that the optical activeness is because of the spatial arrangement, the difference of the spatial arrangements of atoms attached to a tetrahedral carbon, that is sp3 hybridized carbon, if the bonded elements are of different. The 4 elements bonded to a tetrahedral carbon are different. That type of compound shows optical activeness. The carbon, if a tetrahedral bonded carbon is bonded to different types of atoms, that carbon is called an asymmetric carbon, or is also known as stereocenter. If the X, Y, A, B are different elements attached to this carbon, this cause the presence of this carbon cause the optical activeness of the entire compound. And this carbon is called the stereocenter or chirality. It shows the chirality. And this carbon is called asymmetric carbon. For example, in case of the compound in which carbon is attached to bromine also. Bromine. This can be named as 2-bromo, 2-chloro, ethane. And in this case, the carbon is an asymmetric center, and if you imagine a mirror image, a configuration of just as the mirror image of this compound as carbon and hydrogen. This configuration is of mirror image of this first one. And these two are called enantiomers. These two can be not superimposable with each other. That is, if you rotate or tilt this structure of this enantiomer, we cannot superimpose the second one over the first one. This type of compounds have this type of structures are called enantiomers. And this enantiomer, if rotate the plane polarized light to clockwise direction in some angle, the other enantiomer will rotate the plane polarized light to in anti-clockwise direction for the same extent, same angle of extent. That is, angle will be the same, but one will rotate the plane polarized light in clockwise direction and the other will rotate the plane polarized light in anti-clockwise direction. This type of phenomenon is called optical activeness, and the isomers are called optical isomers. And the optical activity is because of the presence of an asymmetric carbon, or this is called, the phenomenon is called chirality. The structures which have non-superimposable mirror images are called chiral structures, or the phenomenon is called chirality. Our hand, the left hand and right hand are of mirror images. The left hand is the mirror image of the right hand, and the left hand cannot superimpose over the right hand. Okay, that is, this type of structures are called chiral structures.
To know about the chirality, let us take a picture of a leaf, an asymmetric leaf, that is, have no plane of symmetry and or axis of symmetry. When it is placed in front of a mirror, we get the mirror image as seen, and the mirror image, if it is placed above the leaf, it is not superimposable over the leaf. This type of objects which has non-superimposable mirror images are called chiral objects, and the phenomenon is called chirality. But in case of this type of a figure, if it is placed in front of the mirror, we get the mirror image of this object, and when it is placed above this object, that is, when the mirror image of the object placed above this object, it can't superimpose, but after rotating to some angle, it exactly superimposable over the original object. This is called a chiral object and is called a chiral. Let us check the chirality of some English alphabets. O letter has a superimposable mirror image, and therefore it is an achiral object. Like that, the letter capital H also have a superimposable mirror image and can be said as achiral. A mirror image of the letter P cannot superimpose is a chiral object. And another example for an chiral alphabet is S. If we place the mirror image of the letter S, it cannot place exactly above the, and it is also a chiral object. This type of objects which have no, that is, elements of symmetry, axis of symmetry or plane of symmetry, are chiral objects, and the molecules which show chirality have optical activeness and have enantiomers.
And if one of the chiral structure rotate the plane polarized light into clockwise direction, it is called dextrorotatory and is represented as D or with the sign plus. And then the other isomer will certainly rotate the plane polarized light in the opposite direction, that is anti-clockwise direction, and is called the levorotatory and is represented as minus sign. We cannot predict from the structure which is dextro or levo. It can only found out by experimentally. And the chirality of, in case of organic molecules, is because of the asymmetric center, asymmetric carbon, presence of asymmetric carbon. And for the asymmetry, the bonded, that is the 4 bonds to the asymmetric carbon is bonded to different elements. And for example, in case of the compound OH, it is ethanol. In case of ethanol, there are 2 hydrogen, same hydrogen, and if we consider the mirror image of this compound, this is the Wedge dash formula for representing through ethanol. And here this carbon is not asymmetric carbon because the bonds, 2 bonds are bonded to same hydrogen atoms. As we put this second structure over the first one, this is not superimposable, but by mere rotation of this structure, we can place the second figure on this first figure, and therefore this is a chiral. And for chirality, the bonds are to different groups. For example, if it is C2H5, it is 2-butanol. This second carbon is a asymmetric carbon to which the hydroxy group, methyl group, hydrogen and ethyl groups are attached. And because of the presence of this asymmetric carbon, it have a chiral structure. That is not superimposable mirror image. We cannot superimpose this mirror image by itself or by simple rotation over this structure, the first structure. And this type of structures are called chiral, and the phenomenon is called chirality. And if the molecule have a chirality, then it behaves as optical isomer, and one of the optical isomer rotate the plane polarized light into clockwise direction, and the other will rotate in anti-clockwise direction. And it is represented by, the dextro is represented by D or with a plus sign, and levo represented by L, small letter L or a minus sign. And if there are these 2 type of isomers, optical isomers are called enantiomers. And if the two isomers, the dextro and levorotatory enantiomers, are present in solution in 1:1 ratio, that solution is optically inactive. That is, one of the rotation is cancelled out by the other rotation. And therefore, that mixture is called a racemic mixture. Racemic mixture. The mixing up of dextro and levorotatory of a compound to make it optically inactive is called the racemization. And the mixture is called a racemic mixture. And the racemic mixture is represented as plus and minus sign. Plus and minus sign. Racemic mixture. The SN1 and SN2 reactions of optically active halides. For example, in case of this common CH3CCl HC2H5, it is 2-chlorobutane. 2-chlorobutane, and here this carbon is asymmetric carbon as it is bonded to different groups. And we can draw the wedge and dash formula of this compound as CH3. And this compound on SN2 reaction, SN2 mechanism with a nucleophile OH minus. OH minus first forms a transition state in which both chlorine and OH minus bonded partially to this carbon. And this OH minus, the nucleophile, can only approach this carbon through the opposite side of the chlorine. And therefore, the transition state will be as a partial bond to OH minus. Okay. And on breaking of this carbon-chlorine bond, it forms the H5. This 2-butanol, butan 2-ol, has an inverted configuration from this parent chlorobutane. Inverted. That is, the position of OH minus OH group is just opposite to the chlorine leaving from this chlorobutane, and the configuration is just inverted. But in case of SN1 mechanism, 2-chlorooctane, it will undergo SN1 mechanism as there is a bulky group present in this molecule, and this carbon is an asymmetric carbon, and we can draw the structure of this chiral molecule as C6H13. The first step of SN1 mechanism is not involve the nucleophile, just the cleavage of carbon-chlorine bond to form a carbocation as carbon with the H, CH3, C6H13 with a positive charge. And this carbocation can attack by the OH minus radical from the opposite side of the Cl, or it can attack this carbocationic side from the same side of the chlorine is left. And therefore, the structure may be, if it is attack the OH minus attack the carbocationic side from the opposite side, that's as H, as an inverted configuration as the parent, or if in the same side OH minus attacks at the same side of the leaving group, then the structure of this butanol, the alcohol, that is the octan 2-ol will be as OH H. That is, there is a two enantiomeric forms of the product, and if these two enantiomeric forms are of in 1:1 ratio, the solution will not show any optical activeness, and that mixture is called a racemic mixture. There is a chance of inversion in configuration and also retention in configuration. And one will be dextro-rotatory and the other will be a levo-rotatory. And if the mixture contains 1:1 ratio of this both dextro and levo-rotatory, the solution will be optically inactive and the mixture is called racemic mixture. Okay.